This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2017 AP Calculus exam, free response question AB5. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions presented in these guidelines, not how the points were awarded. Now, even though this question was not calculator active, I'll consider some solutions using technology. Using technology to solve these problems numerically and/or graphically can provide additional understanding and comprehension of some important calculus concepts. And because these free response questions are usually very comprehensive, I'll suggest some problem extensions. These are additional AP Calculus type questions associated with the information given in the problem, and some of these may be calculator active. In this problem, two particles are moving along the x-axis. For t in the closed interval 0 to 8, the position of particle p at time t is given by the function x sub p, and the velocity of particle q at time t is given by the function v sub q. And we also know that particle q is at position x equal 5 for time t equals 0. In part A, we need to find the times at which particle p is moving to the left. And in B, we need to find all the times during which the two particles are traveling in the same direction. In part C, we need to find the acceleration of particle q at time t equal 2. And then we need to determine if the speed of particle q is increasing, decreasing, or neither at time t equal 2. And then finally in part D, we need to find the position of particle q the first time that it changes direction. Here's a quick look at the scoring standard used at the AP Calculus reading. And remember, I'm going to focus on the solutions, not how the points were awarded. Part A was worth 2 points. First, we need to find the derivative, x sub p prime of t, using the chain rule. Then we need to determine where this derivative, the velocity of particle p, is 0. And finally, we need to identify the interval in which the velocity is negative. Part B was also worth 2 points. And a nice way to answer this question involves sign charts, one for the velocity of particle p and one for the velocity of particle q. We can then examine these sign charts and find the intervals in which the signs of the velocities are the same. Remember that a sign chart alone is not sufficient justification or explanation. A written explanation is necessary. Part C was worth 2 points. To find the acceleration of particle q at time t equal 2, we first take the derivative of v sub q, and then we evaluate this acceleration function at 2. To determine whether the speed is increasing, decreasing, or neither, we need to consider the sign of the acceleration and the sign of the velocity at time t equal 2. We just found a sub q of 2 is equal to minus 4, which is less than 0, and we can either evaluate v sub q of 2 or use the sign chart in part B to conclude that v sub q of 2 is greater than 0. Because the signs are different, the speed of the particle is decreasing at time t equal 2. Part D was worth 3 points. The sign chart in part B shows that particle q first changes direction at time t equal 3. Therefore, we need to use the fundamental theorem of calculus, or the net change theorem, to find the position of particle q at time t equal 3. This position of particle q is equal to the initial or the start position plus the accumulated net change in position. So we need to find the antiderivative of a polynomial, evaluate it at the upper and the lower bounds and subtract, and add the initial position. Here's a way to solve part A using technology. First, I defined the position function x sub p of t. Then I found the symbolic derivative of x sub p. Using technology, I don't really need to see this derivative explicitly. I can simply solve the equation x sub p prime of t equals 0 for t. Next, I graphed the velocity function of particle p. This isn't quite the same as a sign chart, but it's pretty easy to see where the velocity is negative. So the particle is moving to the left for 0 less than or equal to t less than 1. To solve part B, I started by defining the function v sub q of t. If I wanted to create a sign chart by hand, I could start by factoring v sub q and then use the principle of zero products. But I could also instead use the solve command to find the velocity function is 0 at t equal 3 and t equal 5. I then graphed both velocity functions in the same viewing window. I know those times at which each particle has velocity 0. And although this isn't a typical sign chart, it is again pretty easy to find the intervals on which both velocities have the same sign. So both particles are moving in the same direction for t between 1 and 3 and for t between 5 and 8. Part C is pretty easy using technology. Although not necessary if I'm solving this problem using technology, I can find the symbolic expression for the acceleration of particle q. However, I could just evaluate the acceleration, the derivative of the velocity, of particle q at time t equal 2. And then I can evaluate the velocity of particle q at time t equal 2. And since the signs of these two values are different, the speed of the particle is decreasing at time t equal 2. From our work in part B, we know that particle q changes direction for the first time at time t equal 3. We could start by finding a symbolic antiderivative of v sub q of t. However, we could instead just find the net change in position of particle q over the time interval 0 to 3. And then we could add this to the initial or start position. Or we could simply find the position of the particle on one command line. So finally, the position of particle q at time t equal 3 is 23. Here are some extensions to this free response question. Additional questions based on the given information. In this example, let's find the average value of the acceleration of particle p over the interval 0 to 8. Using the definition of average value, this is 1 divided by 8 minus 0, or 8, times the definite integral from 0 to 8 of the acceleration function. An antiderivative is the velocity function. So we just need to evaluate the velocity function at 8 and 0 and subtract, and then multiply by 1/8. Using technology, I first defined the velocity function and then verified the value of this function at 0 and 8. And the average value is just 1/8 times v sub p of 8 minus v sub p of 0. In this example, let's find the speed of particle p and the speed of particle q at time t equal 4. Here's how I solved this problem analytically without technology. I need to use the fact that speed is the absolute value of the velocity. And I found the velocity of particle p in part A. So I first found the absolute value of the velocity at time t equal 4, and then the velocity of particle q is given. So I found the absolute value of v sub q of 4. Using technology, remember that I've already defined the functions x sub p and v sub q. So I found the absolute value of the derivative of the position function of p evaluated at 4, and I found the absolute value of v sub q of 4. The speed of particle p is 1/3, and the speed of particle q is 1. I think this example is pretty cool, and one in which you really need to use technology. For t in the interval 0 to 8, find all the times during which the speed of particle p is greater than the speed of particle q. The speed is the absolute value of the velocity. So I started by graphing both speed functions. The graph of the speed for particle p is in blue, and the graph of the speed for particle q is in red. Bluntly, I need to find those intervals on which the blue graph is greater than the red graph. And I can see two intervals on the graph, but I'll need to find the points of intersection. I used the built-in calculator function to find and label the points of intersection. And the two intervals I need are 2.860 to 3.173 and 4.822 to 5.147. In this example, let's find the total distance traveled for particle p over the interval 0 to 8. Now, I think this is a good question because students need to know the difference between total distance traveled and total displacement. The total distance traveled is the definite integral from 0 to 8 of the absolute value of the velocity. In order to solve this problem by hand, we first need an equivalent expression for the definite integral without absolute value symbols. And that means we need to know where the velocity is positive and where it's negative. Given our earlier sign chart analysis and the graph of the velocity function, we know that the velocity is negative on the interval 0 to 1 and positive on the interval 1 to 8. So I can rewrite the total distance traveled as two separate definite integrals, using the definition of absolute value. An antiderivative of the velocity function is the position function, so I used the appropriate bounds and simplified to get the natural log of 580 divided by 81. And look how easy this is with technology. I can find the definite integral of the absolute value of the velocity function, and the result is the exact symbolic answer. In this example, let's graph the position, velocity, and acceleration functions for particle p over the interval 0 to 8. And let's explain the relationships among the three graphs. If I start to solve this problem by hand, I'm given the position function for particle p. And in part A, I found the velocity function for particle p by taking the derivative of a natural log function and using the chain rule. To find the acceleration function, I need the derivative of the velocity function. And here that means I need to use the quotient rule. Using technology, here's how I defined the position function for particle p, and then I found and defined the velocity function for particle p, and then I found and defined the acceleration function for particle p. Here are the graphs of these three functions in the same viewing window. And here are some observations concerning the relationships among the three graphs. You might also try to describe the relationships when the velocity is 0 and when the acceleration is 0. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions and of how to use technology to solve some of the parts of this problem and to explore, confirm, and visualize results. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.